Welcome back. This is the third part of our lecture 3 of our course Introduction to Complex and Algebraic Geometry. So we continue with the study of Cauchy's integral formula. Previously, we learned about the statement, why it's very important, and we were on track to prove this statement, right? We're going to continue with that. So just a very quick review. We learned if we have a function f defined on some region U inside C to C, that f is holomorphic. We learned that if we pick any point z naught inside U and some radius epsilon, so that the disk centered at z naught with radius epsilon, with its boundary, they completely fall within the region U, right? So this was our U inside the complex plane C, and we picked some point z naught here and some radius epsilon so that this disk would be inside U. Then we learned for any point A inside the interior of this disk, so A should be somewhere, let's say here, but it's not on the boundary. We learned Cauchy's integral formula says the value of the function f at A is determined by the value of the function on the boundary of this disk. So it's given by an integral f of z over z minus A dz, where z is a variable on the boundary of the disk. And we said this is actually quite remarkable, that the value of the function at a point is determined by the value of the function at some other points. And this is not the case for functions which are differentiable in the real sense. However, for holomorphic functions, this holds. And we learned two important facts. The two essential things we learned that we are going to use in order to prove Cauchy's integral formula was that, one, if you have a function f that is holomorphic, so if you have a holomorphic function, and we have a closed curve C inside U, so this is, again, say this is our U, and let's say C is the smooth closed curve here, we learned integral of f along C is 0. We learned integral of f along the curve C is equal to 0. And we saw this is an application of Green's theorem, right? This was the fact number 1. Fact number 2 was a very simple computation. We saw integral of 1 over z minus a dz over a disk centered at some point z naught with some radius epsilon. If we integrate along the boundary of that, it would be equal to 2 pi I when we have a disk centered at the point z naught with some radius epsilon, where A is a point, again, in the interior of the disk. That's the essential thing, right? When A is inside the disk, note that this is not holomorphic anymore, right? Not holomorphic because at the point A, the denominator is going to blow up. It would be infinity, right? The denominator would be 0. The whole thing is going to be infinity. So it's not holomorphic. It has a singularity at A. But we kind of computed this explicitly to see the integral is equal to 2 pi I. Now we are going to use these two facts to prove this formula, the Cauchy's integral formula. Okay, so we want to show that 1 over 2 pi I integral on the boundary of the disk centered at z naught with radius epsilon, f of z divided by z minus a dz is equal to, this is what we want to show, f of a, right? That's the goal. Okay, let's focus on this integral. Essentially, we want to compute this integral, right? We want to say this integral is equal to 2 pi I f of a. So we want to compute integral of f of z over z minus a dz on the boundary of this disk. Okay, there is a kind of a simple trick here. We should rewrite the numerator as f of z minus f of a plus f of a. Well, you know, minus f of a plus f of a, they cancel each other. It doesn't essentially change anything. So I'm allowed to add and subtract. But that would be useful because now I can break the integral into two pieces. One piece would be f of z minus f of a, and the other piece would be f of a over z minus a. We can actually break this into two different integrals. So I just denoted this with di just to summarize things. Okay, so the integral I'm looking for would break into two integrals. What is the value of each integral? So let's call this one integral number one. Let's call this one integral number two. I should compute each integral and see what they would sum up. And the hope is that they would sum up to 2 pi I f of a, right? So integral number one. What is the integral of f of z minus f of a over z minus a dz, where z is in the boundary of this disk? Okay, so here I have my disk at z naught, right? And a is a point inside. So what is this integral? Let's rename this. Let's call this, I don't know, let's call this g. A is fixed, so it's only a function of z. So integral of g of z dz over some curve. Let's call the boundary also, let's denote the boundary with c, right? It's a curve. So this is the curve c, it goes counterclockwise. So I want to use the fact we learned that the integral of holomorphic functions along closed curves is equal to zero. I want to use that. However, you might argue, you might question, is G really holomorphic? Is it? So let's look at this. F of z minus f of a, z over z minus a. Well, f is holomorphic. That was the assumption. So f of z is holomorphic. If you subtract the constant, it still would be holomorphic. Z minus a is holomorphic everywhere in the denominator. The only potential problem, which might cause difficulty and might be a reason that this is not holomorphic, is when z is equal to a. You might say when z is equal to a, the denominator is zero. We are dividing something by zero. It's a singularity, right? It's not holomorphic. But the point is that when z is equal to a, the numerator is also equal to f of a minus f of a. So this is a classical example of 0 minus 0. So the question is that, is it a removable singularity or non-removable singularity? Right. The point is that even without the use of Cauchy's integral formula, we knew holomorphic functions and complex differentiable functions are the same. When z is converging to a, this fraction f of z minus f of a, z minus a, this doesn't really blow up. In fact, this converges to derivative of function at the point z, right? By definition, this limit would be the derivative of function. So even at the point z equal to a, this is a removable singularity. So rather than just defining g to be this, if you want to be very careful, you can say I define g of z to be f of z minus f of a divided by z minus a when z is not equal to a. And when z is equal to a, I define it to be f prime of z. This is the natural way of thinking about it. This is essentially removing singularity of a removable singularity. If I do so, what would I get? Let's go back. G is equal to f of z minus f of a divided by z minus a on C. On the curve C, these two are equal because z is not equal to a on the curve C. So g is equal to this function on the boundary. So they're integrals. They are equal on the boundary. However, the function g I defined this way is holomorphic. So its integral on a closed curve is zero. So if we go back, this integral is 0. And if we go back, we learn this integral vanishes. So it only remains to compute the second integral. Okay, let's do that. So the second integral is integral of f of a divided by z minus a dz, where again, z is in the boundary of our disk. Well, a is a fixed point, so f of a is a constant, so it comes out of integral. And this is what remains. But this is exactly the integral we computed. We learned this is equal to 2 pi I, right? So the second integral is equal to f of a times 2 pi I. First integral was equal to 0. The second integral is equal to f of a times 2 pi I. So the whole integral of f of z over z minus a dz, the boundary, is equal to 0 plus f of a times 2 pi I, or in other words, f of a is equal to 1 over 2 pi I integral of f of z over z minus a dz on the boundary. This is exactly what Cauchy's integral formula claims. So here we have it. This is the complete proof. So I'm going to close this lecture with a generalization of Cauchy's integral formula. Generalization of Cauchy's integral formula. So in fact, you can find this in the book by Griffiths and Harris. So if you have a function f defined on some domain U to C, but let's say you only know it's differentiable in the real sense with integrable derivatives, but not necessarily holomorphic. So let's say we don't know it's holomorphic. We just know it has derivative with respect to z and z bar, but we don't know it's really holomorphic. So remember, being another way of saying a function is holomorphic was its derivative with respect to z bar is equal to 0. Let's say we don't know that. We can compute its derivative with respect to z bar, but it's not necessarily equal to 0. Let's say, or at least we don't know that, right? So let's say take that, consider that setup. Then in the same situation, if we have some u and some point z naught, and I pick some disk with some radius epsilon around that, and I pick another point a, can I say what is f of a in terms of an integral without the assumption that f is holomorphic? Does it have an integral expression? The answer is yes. It's equal to exactly what we learned. 1 over 2 pi I integral of f of z over z minus a dz on the boundary of this disk. There is a second integral which appears in the formula. The second integral is equal to 1 over 2 pi I. And then rather than a one-dimensional integral, we have a double integral over the whole disk, not just its boundary, but the whole interior of the disk. The integral of derivative of f with respect to z bar dz wedge dz bar z minus a. So there is an extra integral which appears here. First, a few remarks. Remark number one, note that if f is holomorphic, Cauchy-Riemann's formula, there was a different way of writing them. If you forgot, you should review that. You can go back to the lecture we discussed this. Would say if f is holomorphic, that means f being holomorphic means this quantity is 0, which would imply this would vanish. So this really is a generalization. It gives back the original Cauchy's integral formula. Remark 2, this is not as interesting as the original Cauchy's integral formula. So the Cauchy's integral formula was interesting because if it was telling us if f is holomorphic, then the value of f at a point is determined by the value of the point at some other points, in particular by the value of f on boundary. This is not the case here anymore, as we would expect. If f is not holomorphic, then the second integral is integrating over the whole disk, which I mean, the point A is one of those points which would appear in the integral, right? So it's not telling you what is the value of f at A based on the value of f at other points. So it's not as interesting. However, this is the version of Cauchy's integral formula we used to prove analytic functions are holomorphic. There are simpler proofs. I actually mentioned them. However, in the original proof that appears in Griffiths and Harris, they use this version of Cauchy's integral formula to show analytic implies holomorphic. And in fact, this is more used for estimations and things like that. We are going to prove this when we discuss kind of complex valued differentiable forms. We haven't discussed that much, so I'm going to ignore this at this point. I'm not going to prove this. Later, when we discuss complex value differential, we are going to see this is in fact an application of Stokes' theorem, which kind of makes sense. We proved the original version of Cauchy's integral formula using Green's theorem. Stokes' theorem is also a generalization of Green's theorem, so that kind of makes sense. Okay, this is a good point to stop.